Hello everyone. So, let's continue exploring this new arithmetic system of modular arithmetic with the following problem. Build a row, a 10-row grid, 4 integers in each row. Make the leftmost integer in the top row 10 and count upwards. The first two rows should look like this: 0, 1, 2, 3. Next row, 4, 5, 6, 7. So, I'd encourage everyone, before they watch the video, to try the problem out on their own. All the problems in these videos are pretty much meant to be solved independently, and then we'll go over the meaning of it afterward. So, I'm going to assume in this case you've given it a shot, and we get the following grid you could think of. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the way for 10 rows. So it's a 10 by 4 grid. Which integers in the grid are in the same column as 0? So if I look at the 0 column, right? In fact, let's make this more looking like a nice table. So if we take a time to look at the 0 column and see if you can figure out what exactly is going on there. And why not? Kind of a little close, but whatever. Alright. So let's look at that 0 column. What values are in here? Well, we have 0, 4, 8, 12, 16, 20, 24, 28, 32, 36. So what is the pattern with all of these integers? And remember, integers just mean whole numbers. Well, seems like they're all multiples of 4. 4 times 0 is 0. 4 times 1 is 4. 4 times 2 is 8. Times 3, 12. Times 4, 16. Times 5, 20, etc., etc. So I'm going to claim that these are all multiples of 4. Which multiples of 4 are just 4 times like any number, right? So I can kind of think of this as 4 times some integer n. So I'm going to call this the 4n column. 4 times any number will get me a value in this column. And if I were to extend in a negative direction, it would fit as well too. So, what integers are in the same column as 1? Well, we have 1, 5, 9, 13, 17, 21, 25, 29, 33, 37. Well, looking at the numbers on their own, it might be, it's not impossible to derive the pattern, but if we look at them in relation to the previous column, the difference is clear. 0 plus 1 is 1, 4 plus 1 is 5, 8 plus 1 is 9, 12 plus 1 is 13, and we can go on and on. So they are multiples of 4 added with 1. Now, if I were to think of it in terms of like a formula, well, 4n is multiples of 4, so we just add 4n with 1. So 4n plus 1. and that would generate anything in that column. Part C says which integers are in the same column as 2. Well, again, comparing it to the original multiple of 4 column, 0 plus 2 is 2, 4 plus 2 is 6, 8 plus 2 is 10, 12 plus 2 is 14, etc. So this would just amount to 4n plus 2. And it multiples of 4 added with 2. And we can probably guess from the last part, it's going to be multiples of 4 added with 3. So 4n plus 3. Now to kind of get us ready for some of the future, 4n, multiples of 4, can be thought of as like 4n plus 0, where we have added no values. We have added no values to multiples of 4. Now, let's take a look at those numbers we're adding. 0, 1, 2, and 3. Well, we just learned about the modulo system, where we start at 0 and end at the amount of terms the modulo is in. In this case, we have 4 terms, 0, 1, 2, and 3. So we could think of this system as modulo 4. And these numbers on the end of each formula, the plus 0, plus 1, plus 2, plus 3, well, they are all possible remainders when dividing with 4. Because you can't possibly have a remainder of 4 when dividing with 4, because that would just generate another whole number. So, one way to think of division is in terms of this thing called the division algorithm. And the division algorithm states we have, for two numbers, a, and, or not for two, we're just going to say a is equal to let me stick with what I'm using. So b times n plus r, where n is going to be like my quotient, my result after division, and a is my dividend, b is my divisor, r is going to be my remainder. And we can think of like all of these patterns as being in the following form. A is equal to, our b in this case is going to be 4 times our n plus the remainder, where r is greater than or equal to 0, but less than 4. Because our only possible remainder is 0, 1, 2, or 3. Now, let's look at part E. If you were to extend the grid to 1,000 rows, would the integer 3,713 be in the same column as 0, 1, 2, or 3? So, I'm gonna, like, the way we're probably all taught to divide is with long division. We probably haven't been taught the division algorithm in grade school or anything like that. And I'll probably make a video in the future going into more detail about how this all works. But I'm going to show you both ways how to do it, starting with the division algorithm. So, in this case, 3,713 is my A value. And that equals 4 times some number plus whatever the remainder is. And we know the remainder is going to be 0, 1, 2, or 3. Now, what number times 4 is going to be pretty close to 3,713? Well, if we do 4 times 928, we get a number that's fairly close. 4 times 928 is the same thing as 3,712. So therefore, to get to 3,713, we would simply have to add a 1 to it to complete the result. And now what this tells me is that since we have something in the form of 4 times n plus 1, it's going to belong in the same column as 1. Because that is, it's the same formula, or same expression in this case, I guess, where n is 928, and we have this remainder of 1. So somewhere down the list is 3,713. Now, what we could have done, and the way you probably did it if you try to do it on your own, is just do the normal division. So if I take 4 and divide it with 3,713, I know that 4 would go in 37 9 times. I'm going to get 36. Subtract a 1, drop a 1 for 11. Then we'll go to 11 twice because we get 8. Running out of room. That result would be 3. 3. Drop the other 3. So we have 33, sorry. And now how many times does 4 go into 33? Well, that would be 8 times, with 32 as our 4 times 8, and we get a remainder of 1. So it'd be 928 R 1, just like we got in the division algorithm. A little bit messy. And we could have figured out, all right, if it had a remainder of 1, it's going to be in the 1s column. So what does this all get us to? Well, we say that two integers are congruent or equivalent modulo m when their difference is a multiple of m. Otherwise, they are incongruent modulo m. So in this problem, we have discovered that 3,713 is congruent, we write that with the 3 lines, to 1 modulo m, or modulo 4 in this case. They are the very same. Now, what does it mean by if their difference is a multiple of m? Well, if we simply do the difference, meaning subtraction, 3,713 minus 1 over 4, is this a multiple of m? Well, yes, we do 3,712 divided by 4, subtract the numerator, and we know that that is the same thing as 928. So that's 928. 928 is a multiple of 4. Okay. Now, where does this all come from? Well, again, if we think of the division algorithm, where we had, how did I write it out last time? A equals B times N plus the remainder. And it's not always plus the remainder, but oftentimes it is. So I'm just going to put R. You could put any variable there, but here's how it works. In this case, we declared that A was 3,713, and our 1 was our leftover remainder, and the 4 in this case was what B was. Now, if I subtract R on both sides of this equation, we have that A minus R is B times N. Well, isn't that what the congruence is saying? The difference of our numbers A and R, 3,713 and R1, was a multiple of 4. Or in this case, I should really write B as M. In this case, if we're going to adapt everything for the modulo system, our B in this case, or B is really M in this case, modulo B times N, or M times N. So if A minus R is equal to M times N, then it has to be a multiple of M, because whatever integer this ends up being is literally has M as a factor of it. And to kind of fit it along with what we did on the left hand side, if I divide my M on both sides, well, the formula then simplifies to A minus R over M is equal to some integer N, which is the process we just did. Now, to find some more examples, we have that, for instance, 8 is congruent to 28 mod 4, right? So if I find the difference of 8 and 28, we can do 8 minus 28, which is equal to negative 20. And negative 20 is definitely a multiple of 4. It's 4 times negative 5. So yeah, they are definitely congruent. You can check with 17 and 33. But let's look at some counter examples, like 12 and 7. If I try 12 minus 7, well, I know that that would be the same as 5. Now 5 is certainly no multiple of 4. So not a multiple of 4. So therefore, we have that 12 is not congruent to 7 mod 4. And to define things even further, if we have some A congruent to B mod M, this is true if and only if the difference, again, is a multiple of M. And in this it expresses as K, right, instead of N, like I did. Well, it doesn't matter. We divide to get the following formula. So we say that A is congruent to B mod M if and only if a minus b divided by m is an integer like k, where k is an integer. So what this theorem is stating is that if this is true, then we have that a is the same as b mod m. Or it's also saying that if we already know that a is equal to b mod m, then this is true. This formula is true as well. So it works in both directions. One thing leads to the other in either situation. And in the future problems, we'll explore exactly how we can take advantage of this fact.